Hi, so we'll be learning about the need of semaphores today in operating system. Okay, so as you can see here, this is a shared variable called x and basically it represents the number of likes on a YouTube video, and currently the number of likes is 100. Okay, so let's say two different users like my video, and the count should go from 100 to 102. Okay, now there are two processes that spawn up for each user. So user 1 has liked the video, so this process is spawn up and it tries to increment the value of x by 1. Okay, and similarly user 2 has liked the video and a new process is spawn up which also tries to increment the value of x by 1. So now here these two processes run simultaneously. Okay, now before we understand about the problem, the issue that lies here, let's talk about what are atomic instructions. So here x is equals to x plus 1 is not an atomic instruction. Why? Because this is because the CPU can be interrupted in between this instruction as well. So you can't say that once this instruction is finished, only then another process can come in and start its execution. No, because this instruction is composed of these three instructions. Okay, one, two, three. So it is possible that only after the execution of step 1, the CPU may take up another process called P2 and it starts its execution. Okay, so what I am saying is that so let's say uh, P1's first step is executed. Okay, and then P2 comes in and its first step is executed, and P2's two step is executed, and then P1 again comes in and its second step is executed. So as you can see, P1's one and P1 second step are a part of same command that you have wrote. So in your code you have written x is equals to x plus 1. Okay, but this instruction, or basically this command, won't be executed in a single run. So these are the processes that are executed by the CPU, and it may happen that the one process once only first step is executed, and then a P2 takes up the CPU. Okay, so that is why this instruction is not atomic, but these instructions are. So this instruction, uh, if a CPU is executing this instruction, then only after this instruction execution is finished, okay, only then it is possible that another process may take up the CPU. Okay, may take up the CPU, but for this instruction, it is possible that in between the exec before it is finished, the CPU can take up another process as well. Okay, so now let's understand about these three instructions. So first of all, x is residing in your main memory. Okay, and its current value is 100. Okay, so now first step, there is a register. So now there is a CPU. Okay, and with the CPU there are many registers. Okay, R1, R2 and so on. So these registers are easily accessible by the CPU. Okay, so basically the cost of fetching values, okay, reading data from registers is very less. Okay, and So therefore in the first step it reads the variable x into the r1 register. Okay, so into r1 register it reads the value of x, which is 100. And in second step, so now here r1 would become 100. Now r1, now it will operate on r1. Okay, now it will increment by 1, so it will become 101. Okay, from 100 it will become 101. And in the third step it puts back the value of r1 into x. Okay, so now this value is put back to x in the main memory. Okay, so now this becomes 101. So this is how your this simple looking command x is equals to x plus 1 works in real life uh, by splitting your command into three more smaller instructions. Okay, now let's understand about the problem. So this is your P1 process and P2. Okay, and this is your the execution timeline. So now let's suppose P1's process reads the value of x, okay, into r1. Now first is this. Now r1 would be, let's maintain the values here. Okay, so now r1 would become 100. Okay, r2 is nothing and x was 100 initially. Now in the second step, now so let's also see the CPU here. This is CPU. So first P1 was executing. P1 executed this command and P1 leaves. Now P2 comes. Now P2 will also start executing. R2 is equal to read from X. Okay. Now X is initially 100, is also 100 now. So R2 will become 102. Okay. And now again, now the CPU, the process P2 will continue executing. So this is a theoretical scenario. You can assume any sequence of your steps. So R2, now what was the second? R2 is equal to R2 plus 1. So R2 would become 101. Now P2 leaves the CPU and P1 takes in, and P1's step was R1 is equal to R1 plus 1. So it will also become 101. Okay, and now now the CPU is again with the R1 only. So it will put back the value of R1 into X. So X is equals to R1. So now X would become 101. So now as you can see in our process, this was the only instruction, and it was composed of three smaller atomic instructions, and all three atomic instructions have been completed. So our process exits. Now P1 will have to leave the CPU. Now P2 comes. So now here P2 comes and it executes. It puts back the value of R2 into X. Okay, so what was in R2? 101. So it will put it into X, which is 101. Okay, so now P2's execution is also completed. So it was completed here for P1, and now it is also completed. So now by the end of execution of both the processes, what is the final value of x? It is 101. So now, now user 1 has liked my video, user 2 has also liked my video. So the count of x must go from 101 to 102. But what is the actual count? 101. Yeah, so this was the issue. And why the issue was happened? Because P1 and P2 uh, can take up the CPU at any point of time. Okay, so therefore they rate the same value of x and hence updated them by one only. Now how could we solve this problem? So now comes the importance of semaphore. So semaphore is a kind of synchronization tool. Okay, it is used to take the lock. by the process, so that these kind of conditions won't happen. Okay, these kind of racing conditions won't happen. So I will just give you a very brief use case of your semaphore here. So you can see your P1 process and P2. So P1, so now let's say both will check both will check a shared variable, let's say called as s. Its s initial value was 1 only. So now P1 will check if s is 1. If s is 1, then it will go on executing the instruction x is equal to x plus 1. Now, similarly here, so this will check if s is 1, and similarly here it will check if s is 1 and go on executing the instruction. And once the instruction is completed, it will increment the value by 1 again, signal s. Okay, so let me show you weight of s. It will decrement the value of s by 1 only if s value is greater than 0. Okay, so s is equal to 1 means your no one is currently operating on shared variable. Okay, what is shared variable? It is x. So no one is operating on shared variable called x. So now let's say P1 comes in and it checks if the value of s is greater than 0. Yes, it is currently 1. So it will decrement it and go ahead. Okay, now let me tell you, wait is an atomic instruction. That means if this particular instruction is being executed, then P2 cannot take the CPU in between. Okay, so therefore there is no chance of racing condition here. And so let's say S was 1, P1 enters. Okay, P1 marks S is equal to 0. Okay, and now let's say P2 enters. Now P2's weight of S function, okay, will check that s is 0. So it won't go ahead. It won't go to next line. It won't go to next line. Okay. So now P1 will execute its instruction. P1 will execute its instruction, that is x is equals to x plus 1. Okay. And then it will signal. Now what signal will do? It will increment the value of s by 1, so that other processes now can operate on shared variable. So now once this happens, uh, this means p1 is saying that have done I have done operating on shared variable. Okay, I have completed my work. So now you can operate on shared variable. Okay, this means incrementing the value of s by 1. So now since s becomes 1, now P2 will check again if s is greater than 0. Yes, so P2 will execute its instruction. Which instruction? Its instruction x is equal to x plus 1. Okay, it checks and it also does decremented by 1, which becomes 0, and executed instruction, and now signal of s would again mark s is equal to 1. It will increment, okay, from 0 to 1. So this way you can see the racing condition has been prevented by using a semaphore. So semaphore is nothing but a synchronization tool. Initially its value is 1. okay, so that only one process can operate on it. So if so now it can happen that P2 may have entered earlier, okay, so in that case P2 will mark the S is equal to 0, and then P1 would have to wait. So first P2 have completed its section, only then P2 could operate on the shared variable. So this way you can use semaphore to avoid racing conditions. Okay.